Today we're going to be talking about intermolecular forces, and we're looking at the different types of intermolecular forces and how they affect boiling points. And the last chapter we were talking about, covalent, ionic, metallic bonds. Those are intramolecular forces inside the molecule. Like this would be a covalent bond here. So today what we're going to talk about is the forces between molecules. They're called intermolecular forces. And I do want to point out that when you talk about total bond strength, like how strong these bonds are, covalent, ionic, metallic are stronger than the bonds between molecules. So we're going to talk about three different ones today: hydrogen bonds, dipole forces, which are actually what holds polar molecules together, and then dispersion forces, which is actually what holds things that are nonpolar together. We say things that are nonpolar don't really have a good way to stick together, so there are a lot of times they're gas at room temperature, but there is a small force that can hold them together, which is how you can have liquid oxygen and liquid nitrogen and stuff like that. So, all right, like I say, we're going to talk about the three different types of intermolecular forces. We'll start with the weakest one, and it's dispersion force. Is what holds together things that are nonpolar. So let's say we have a nitrogen molecule. It'd have a triple bond between them. There'd be electrons here and there. And so when you look at the outsides of it, it's just got electrons going around the outside. So you'd say no matter how you look at it, it would be negatively charged. And so if you brought another one next to it, they wouldn't really stick together. But here's how they actually do stick together and how you can make liquid nitrogen. Each one of these has 7 total electrons. So there's a total of 14 flying around this. You would expect that at most times that you'd have 7 over here and 7 over there because they're sharing electrons equally. But the reality is, when you have 14 electrons floating around, if you were to take a snapshot at some moment in time, so let's say all these electrons are kind of floating around between them, you might actually have 8 electrons over here and 6 over here. And when that happens, 8 over here with a negative charge and only 6 over there with a negative charge, that's called a momentary dipole, where one side is slightly negative, the other side then is slightly positive, and it then causes another momentary dipole in the molecule adjacent to it. And so it gives them, so if another one is over here, it gives them this real weak interaction that allows them to stick together. Now, it's very, very weak, which is why nitrogen, you have to get it extremely cold for it to actually stick together. For these forces to start working, you have to get it very, very cold, and then suddenly the nitrogen molecules will start sticking together, because it's because of the random motion of electrons. And then when you talk about the strength of dispersion forces, the more electrons you have in a nonpolar molecule, the stronger its dispersion forces could be, because you can actually have more distortion. So for instance, like this chlorine here, each one has actually 17 total electrons for a total of 34. So if you took a snapshot at some moment in time, you might have 20 over on one side at some point, and then obviously only 14 on the other. So there's a bigger charge differential there, and so you'd have a stronger force. So the more electrons that a nonpolar molecule has, the stronger its dispersion forces would be, and it would make it easier to then stick together. And so that's what all this is pointing out. Again, more electrons, more electron cloud distortion here, and stronger intermolecular forces. So it says, why are F2 and Cl2 gases at room temperature and Br2 and I2 are liquids? So let's look where they are on the periodic table. So F2 and Cl2 are actually gases, because remember, these are Brinkhoff elements, but Br is a liquid and iodine is actually a solid at room temperature. They're all nonpolar molecules, but what you have is more and more electrons as you go down the table. So F2 would have a total of 18 electrons, and so there's not much distortion between the electron cloud. But down here with iodine, it's got 53, so I2 would have 106 total electrons. And so larger and larger atoms, more and more distortion in their random motion of electrons causes stronger forces holding them together. So gas, liquid, solid at room temperature. More electrons between, nonpolar molecules means they have higher forces of attraction holding them together. And again, I pointed that out there in the answer for you. And then the next thing is you have these attractions between dipole are dipole attractions between polar molecules. And the only problem with this is I didn't realize it when I copied this, but this right here is backwards. This is not going to be true at all. The way they would be attracted would be, again, if you had HCl together, notice this says when they have this side slightly negative and this side slightly positive, those are based off electronegativity values. Chlorine's got a higher electronegativity than hydrogen, and electronegativity is the attraction for electrons. So when they're sharing electrons, they would hang out closer to chlorine. That should be an arrow there. And we could say the same here. They would hang out closer to chlorine, and so that would be, side would be negative, this side would be positive, and then that's the force that holds them together. That's called the dipole force. So when you have a molecule that is polar, in other words, it's got a positive and a negative side, which these have. Again, this is slightly negative, that's slightly positive, and here this would be negative, and this would be positive. That force right there holding them together, because the molecule is polar, is called the dipole force. And like I say, it's stronger than a dispersion force, because now you got a positive and a negative side of those molecules, so you're more likely to see these molecules hold together better. Like this actually is an example of hydrochloric acid, or hydrogen chloride, but and it sticks together. It can be a liquid at room temperature because of that. Even though it's a really small molecule, it's got that polar bond holding it together. And then the last thing, and the strongest of the intermolecular forces, is called a hydrogen bond, and it's just a special kind of dipole, because you look right there, we have hydrogen here and its interaction with chlorine, but hydrogen bonds only occur, so like I say, they're a special type of dipole. They only occur when hydrogen is attached to the very electronegative elements on the periodic table. And those elements that have the highest electronegativities, you can go look them up, are N, O, and F. Notice these are not included in the electronegativities, so they don't have an attraction for electrons because they're, again, the noble gases. So N, O, and F have the highest electronegativity. So what they do is when hydrogen's attached to them, hydrogen will essentially, the high electronegativity element, in this case, this is oxygen, this is one of them. So again, remember I said N, O, and F, when they're attached to hydrogen, they'll make hydrogen bonds. What happens is oxygen's got an electronegativity value of 3.5. Hydrogen's 2.1. So that when this bond, they're sharing electrons between them, they actually hang out closer to the oxygen, and then that leaves basically just kind of, remember, hydrogen only has a single electron, and that's why this is also unique to hydrogen and not other elements like in column 1, because hydrogen only has one electron. If you steal the electron away, then you have just this proton here that's kind of hanging out almost by itself. And so that proton then will latch on to an adjacent oxygen molecule, because remember, oxygen's, the electrons are hanging out closer to oxygen. It's actually got two unshared pairs of electrons as well. And so that bond holding them together between adjacent molecules is called a hydrogen bond. And again, this only occurs, like if we have the exact same molecule like H2O and H2S, but we substitute sulfur in for oxygen. Sulfur's electronegativity is 2.6. Hydrogen's 2.1. So this sulfur doesn't really steal that electron away. And so that means the electrons can hang out a little bit more closer to hydrogen, and so you don't have that proton sitting by itself. So this bond right here between adjacent hydrogen sulfide molecules would be weaker. And it affects their boiling points, because, you know, the stronger the bond that can hold them together, the higher their boiling points. Water has a high boiling point compared to some other liquids because it's got hydrogen bonds that hold them together. So what this chart is showing you here is this is showing you, because you got to really break down each individual line here. So this is H2O's boiling point, very, very high compared to the rest of them because it's got a hydrogen bond, much higher than hydrogen sulfide because it doesn't have hydrogen bonds. But when you continue to go down the table, so we're talking about H2O, H2S, H2Se, H2Te, so the molecules would be exactly the same, but you have the larger and larger interior elements in them. So if that's the only mechanism that's affecting boiling point, the larger and larger the molecule that's attracting hydrogen, the higher its boiling point to be, because it's kind of harder to break them apart because they're larger and larger molecules. But what's unique here is how far out of place H2O is. Since it's the smallest, you would say, why does it have much higher boiling point to these larger and larger atoms? And it's because they have really small electronegativities. They don't steal the electrons away from hydrogen, yet the oxygen does. And so that's why, you know, the oxygen, or H2O, has a much higher boiling point than it should have. And then if you look at the next one, this is all the elements, HF, HCl, HBr, HI. These are all the elements here, HF, HCl, HBr, HI, as you go down the table that are attached to hydrogen. And so as you go down the table, again, you would expect the boiling point to increase because you have larger and larger atoms, and it's harder to move them. But HF, again, has a much higher boiling point than it should have because fluorine's electronegativity is 4. And so it steals the electron away from hydrogen, and then you have a really strong force between adjacent, you have a really strong force between adjacent molecules because the fluorine can steal that electron away. Oh, because again, its electronegativity is 4, hydrogen's only 2.1. And so it's got a much higher boiling point because of its electronegativity value. So again, and the rest of these are the same, but I do want to point out here, notice with this is the combination of all the elements in column 4. CH4, SiH4, GeH4, as we go down the table, they have higher and higher boiling points because you have larger molecules. It's harder to move them, so it's harder to break them apart. And you don't see CH4 is not out of place because it doesn't have a high enough electronegativity to create what's called a hydrogen bond. Hydrogen bonds are only when hydrogen's attached to NO and F. All right, so it says which would have the higher boiling point. And explain. Now, when you're given these, this is where I get a lot of people that start struggling with some of this stuff because they don't want to do any extra work associated with it. They just kind of want to answer the question or look it up. You sometimes will have to do a dot structure because remember, non-polar molecules have lower forces of attraction than ones that are polar. And the only way you're going to know if it's polar is to do a dot structure. So if you do a dot structure for these, this is what you get. NH3, and then you're going to have some dots there. If you do a dot structure for this one, this is what you get as well. So they're both polar. So when you have, that means you have dipole forces that can hold them together. The only other question then is, does one have hydrogen bonds? Because that's the strongest intermolecular force. Remember, you have hydrogen bonds when hydrogen's attached to N, O, or F. So this one has hydrogen bonds. So again, this has the higher boiling point because of hydrogen bonds. And H2S or H2O, again, you need to do a dot structure for it to know this. I know we just talked about it, so you could probably remember that from what I just said, or I just talked about it. And they're both, now here's the thing, if you do a dot structure for that, you're going to have to visualize that these are actually not linear molecules. These extra pairs of electrons take up more space than the shared pairs. So these molecules then actually end up looking like this. That's what they look like. And they make bent molecules. So they're both polar, but one has hydrogen bonds and one does not. So the answer there, when we say which has a higher boiling point, that'd be H2O because of its hydrogen bond. All right, moving on. Let's see. Which of these has a higher boiling point? Again, when you're looking at these are obviously both non-polar molecules. So they have dispersion forces holding them together, and the one that has the highest dispersion force would be the one that has the most electrons. Each oxygen, again, only has 8. Nitrogen only has 7, so that would have the highest dispersion forces holding together. They're non-polar, more electrons means higher forces. SO2 and CO2, those are, again, like I say, you can't just eyeball this because you could say, well, they seem like they're the same molecule, they seem like they're the same shape, but if you do a dot structure, this is what you get. And again, that's a bent molecule because of those two. CO2, you get a couple of double bonds there, and that's non-polar. So a polar molecule has stronger forces between molecules than one that is non-polar. So SO2 is bent, so that's why it's got a higher boiling point. HF and HI, again, you could really look at that and go, well, they're obviously going to be polar because it's just a hydrogen and another element. They don't have the same electronegativity, so you're going to have a negative and a positive side. So the question there would be, does one of them have hydrogen bonds? And HF would have hydrogen bonds. And then the last one, SiH4 and GeH4, again, this is another one. You can do a dot structure for them. This is what you're going to get. So the molecules then, you need to know that that's tetrahedral shape and just hydrogens on the outside. It's symmetrical. It's going to be nonpolar. And so the strength of the forces that would hold them together would be whichever one has the most electrons for nonpolar molecules, and that would be GeH4. And the last thing here, place these in order of increasing strength of intermolecular forces. And so the strongest would be hydrogen bonds. And so we've got to do dot structures for these to figure out what they're going to do. And so we got SCl2 there. That's what we're going to end up with for that one. NH3, CH4, and then Cl2, obviously. And so it says place them in order of increasing strength. So we want to look at the weakest ones first. And so the weakest ones would be the 2, that would be nonpolar. And the more electrons you have in them, the stronger the forces. So CH4 would have a total, carbon's got 6 electrons, each hydrogen has 1. So that's a total of 10 electrons there. The 2 chlorines, they have 17 apiece, so they have a total of 34. So CH4, nonpolar, fewer electrons. And then Cl2, nonpolar, more electrons. And then after that, so we've got those 2 knocked out. And we've got these 2 here. They're both polar because this makes a bent molecule and this makes a pyramidal molecule. Again, you'd have to look it up to know that for sure. Or anyways, and so when they're both polar, the next question is, does one of them have hydrogen bonds? And this one, hydrogen with nitrogen will make a hydrogen bond, so that would be the strongest of all. And so there you go. SCl2's just got a polar bond, and NH3's got a hydrogen bond. And then the last thing there, which has a higher boiling point, explain these. And again, this makes a polar molecule because those will make it lopsided. But right here, that's got a hydrogen bond on the end of it. And the thing is, these are exactly the same molecules, but they're arranged differently. And because of their arrangement, this one has a higher boiling point because it's got a hydrogen bond in it. And so ethyl alcohol it would be harder to break ethyl alcohol apart than dimethyl ether. So that's it for this lesson on intermolecular forces. Good luck. You've got a total to work on.